So the next paper is from our colleagues from the Karlsruhe Institute of Technology from Germany, and the authors are Carmen, Krahe, Maximilian, Iberl, Alexander Jacob, and Gisela Lanza. The paper is entitled AI-based computer-aided engineering for automated product design, a first approach with a multi-view based classification. We are looking forward to your video presentation.
So then, hello everybody and welcome to the presentation of my paper, AI-based computer-aided engineering for automated product design, a first approach with a multi-view-based classification. So my name is Carmen Krahe, I'm the first author of this paper, and I'm from the Karlsruhe Institute of Technology, especially from the Institute of Production Science, WBK. So what is the current initial situation we are confronted with in our paper? We say that in a lot of companies there exists a large amount of already existing CID models, and those CID models contain a lot of experience knowledge of designers, because those CID models, respectively the corresponding products, have already been successfully produced and sold. The problem is that this implicit knowledge is so far not formalizable, so it's not possible to express this knowledge in rules, and so it can't be handed over to other designers, to new designers, and to unexperienced designers. So what we try to do now is to use methods of machine learning to make this implicit knowledge formalizable. And therefore, we develop some kind of design assistance, which on one hand shall support especially inexperienced designers or engineers in a design process, and on the other hand, which shall relieve designers from repetitive adaptations, for example, caused by divergent requirements, standards, and dimensions. And the idea is then to save time and also costs, and mainly to give the designers more free space for real creative work, which we can't replace by methods of machine learning. So how does our solution looks like? We try to extract common design patterns for different component classes from the existing CID models. And on basis of this, it's the idea to propose next design steps. Or some other thing is to also indicate already existing very similar CID models to the designer in order to avoid the design of duplicates. So our database, just like I said, is mainly contained out of CID models, which contain implicit experience knowledge of designers. On the one hand, in form of pure geometric information, for example, information about the shape of the CID model or the different dimensions, just like height, width, and length. And on the other hand, this is the so-called design history or model tree, which is the sequence of design features a designer used to build up this CID model. And the model tree also contains the corresponding parameterization of those features. And you can imagine a feature, for example, just like extrusion of a cuboid, or a drilling, or for example, a rounding. And what are we gonna do with this information? The geometric information we mainly use for classification task or similarity analysis in our approach, and the design history we want to use to propose really next design steps to the designer in form of next features. So how does our approach looks like? We have a three-stage approach, and the basis for our approach is first to make some component classification in order to categorize the existing database, and so to enable a designer to find a suitable CID model more quickly. And therefore, we first make some classification, and then we try to propose in between one component class the most similar CID model that already exists. So this is the basis. And the next step is then to classify semi-finished components during a design process. This means that our design assistants shall recognize during a designer or designers designing the product which component class is currently under design. And then if it has recognized which component class it is, it shall look in the existing database of this component class if there maybe already exists some very similar CAD model, which is then proposed to the designer in order to avoid the designing of duplicates and to save time. And the next step is then not to propose a complete CAD model, but to propose real meaningful next design steps to the designer. And therefore, we also have to recognize first which component class the designer is currently designing, and then the design assistant tries to propose in this component class real meaningful next design steps, which it has learned from the existing data and the contained design patterns of this data. So here, for example, the designer designs some lid, and the design assistant proposes a next design step in form of a hole. So what we did until now is the basis. So we first considered the pure component classification. So in the existing literature, there are mainly four different state-of-the-art approaches how to represent 3D models to process them with methods of machine learning. So one approach is the so-called multi-view approach from Su et al. And introduced in 2015. Another approach is to use graphs to represent 3D models, for example, done by Simonovsky and Komodakis. It's also possible to use point clouds to represent 3D models, for example, done by Sedergaard et al. In 2017. And the last approach is some voxelization of a 3D model, and you can imagine voxels like a 2D pixel. And for example, Key et al. Used this approach. And all those authors I mentioned mainly used this 3D representation form to make some classification task. So what we did now in our approach, we used some adapted variant of the multi-view approach of Su et al. So what is the goal? Of course, we try to classify components, and the aim is to order the available data to find components more quickly in the existing database. And the classification is also the basis for the classification we want to do with semi-finished components during the design phase. So our approach first defines some kind of standard orientation of the components, which is determined by 5 different conditions. Then we create 2D images of the 3D objects from different perspectives, and the 3D objects therefore were aligned in the standard orientation. And lastly, we classify those 2D images via convolutional neural networks. So therefore, we trained perspective-specific CNNs to classify those 2D images. And as you can see on the picture on the bottom right, we used 26 different cameras, so 26 different perspectives, and combined the opposing perspectives into one CNN. So this means that we had 13 different CNNs for our 26 different perspectives. And in the end, we pooled the perspective-specific class probabilities into an overall forecast. So we made some proof of concept of our approach with the ModelNet 10 database, which was introduced by Wu et al. In 2015. It contains about 4,900 3D models of 10 different categories of furniture, and you can see here in the picture some examples of each category. So first of all, just like I said, we determined some kind of standard orientation with respect to a defined base perspective, as you can see here in the picture. The next step is then to generate 2D images from the different perspectives. In sum, these were 26 different perspectives. Again, you can see it here in the picture, and on the bottom right, you can see the 2D images of a spatial level here on the example of a sofa. And in red, you can see the 2D image of the base perspective. The next step is then to train the perspective-specific CNNs with those 2D images we get in the way I just explained. And the classification is then done by a pooling over all perspective-specific class probabilities. So we summed up all probabilities from the perspective-specific CNNs. So in sum, these were 13 different probabilities for the 26 different images. And then we calculated the average over these probabilities, and this is our final class assignment. So how does our results look like? You can see here on the left the accuracy and on the bottom the perspective-specific CNNs. And as you can see, the accuracy of the single perspectives varies between about 68 and 84%, which is quite much. And we also have large difference depending on our model category. For example, toilets are classified quite well in all perspectives or in all CNNs. But in contrast, for example, tables have a very large scale of the accuracy, or also dressers and or desks. So our overall accuracy we achieved over all classes is about 88.4%. And you can also see it by the red X, it's the overall classification accuracy. So here on the picture, you can see the confusion matrix of our classification task. And as you can see, often the assignment is not clear, especially here in the class desk. Only 58% desks were classified correctly, and for example, 18% were wrongly classified as sofa. So what is the reason for this? We found out that objects often look quite similar from certain perspectives. For example, a sofa and a desk both have a square base, and so both look quite similar from one perspective. For example, you can see it here on these pictures in the third column. We have the class desk from two different perspectives, and from both perspectives, the 2D images were wrongly classified as sofa. So on the bottom right, you can see the picture of a sofa from these perspectives, and probably the CNN learns to link this angle shape more to a sofa than to a desk, and that's the reason why those desks were here wrongly classified. So what is the conclusion for us from this? We found out that the multi-view approach works quite well if the classes are quite different. But for example, on the example of the class desk and sofa, it's necessary to look more into detail, so to try to represent more those inner structures, and therefore in next investigations we, for example, try this classification task with the help of graph-based approaches, which are able to represent those inner structures in more detail. So then, thanks for your attention, and I'm looking forward to your questions later.
Thank you, Carmen, for your presentation. For those of you who has just turned in, we are on live stream 2 of the CIRPe Global Web Conference, Day 1. As next, we plan to have a live discussion with Carmen and discuss your questions you have posted during the video. Other than this, we have another live stream. Also, if you put the link below, live stream 1, where we have started today with the opening session of the conference. So I'm turning left to my colleagues, and I would ask you do we have a connection to Carmen? Carmen, can you hear me now?
Are you able to hear me?
Yes, great.
Yes, okay, cool.
Thank you for your presentation and being with us now. The first question I have is, what are the challenges of industrial applications for your approach?
So there we have several challenges. I would say one main challenge is to integrate our approach into existing CAD software, because in our project we are working with PTC Krahe. It's a common CAD software, and so there we have to investigate special APIs. This is one problem. But I think one major problem is that we first have to gain the confidence of the design engineers, because I talked a lot to engineers and they told me, oh, I'm afraid of being replaced by machine learning. And another thing is that I also want traceability and understandability. So if we, for example, propose next design steps, there's the problem that a designer wants to know why the assistant system says this. And that's a thing we have to work on in future work.
Okay.
And I think, some other point is also that in a lot of companies, the CAD models are labeled quite bad. So for the classification task, which I was presenting in my presentation, we need labeled data, and this is some other problem because, especially the companies we are working with, their databases are more or less unordered. So this is some other challenge we have to meet.
Okay, thank you. Do you compare the perspectives one-to-one or also between different perspectives in order also to connect, for example, with mirrored models?
You mean that we just change some perspectives? I didn't get a question right.
Yes, I mean, do you compare the perspectives to each other one-to-one, or do you have a connection between them, between mirrored or simulated models and also the real perspectives?
So we had 26 different perspectives, and just like I said, we always combine two perspectives, the opposing perspectives. So we had 13 perspectives altogether, and for the classification, we combined all perspectives. So,
okay. Please just go ahead.
I didn't just get a question.
Maybe I can ask our commenters to specify the question. And in the meantime, I would like to ask you about the future work you are going to do. Do you have new approaches based on your results, which are presented in your paper now?
We also worked on a graph-based approach for a classification task, because one problem, like I said, is that only visual view of an object is not enough, because we have to represent the inner structures, and for this we worked on graph-based approaches for the classification. And we also tried some first approaches on proposing the next design steps. Therefore, we use recurrent neural networks, and we trained them based on the sequences we extracted out of the CAD models, especially from the PARC files. So this is the so-called structure tree.
Thanks for your comment. I just see that our commenters type on the chat.
Okay.
So, there's the specification of the second question. Let me just read it to you loudly. Do you compare every perspective with the 26 perspectives of the other product, or just one by one?
No, we just compare one by one.
Okay, thank you a lot for your answers, and thank you for connecting to us today.
So thank you a lot too.
Hope to see you soon. Bye.
Yeah, bye.